Okay, student, today we are going to start the new topic. That is nothing but the simple pendulum. Now, what this simple pendulum is there? Simple pendulum is nothing but a heavy mass is attached to a string. What is the characteristic of this string? Ideally, this string should be light and it is inextensible. Ideally, it should be inextensible and it should be massless. So ideal simple pendulum is a simple pendulum which consists of a heavy mass attached to a string. That string should be massless and inextensible. But practically, it is not possible. So practically, simple pendulum can be defined as a heavy mass, or I can say a point mass, is attached to a string which is light in weight and that string is inextensible. Now this point mass concept is what? That is nothing, a spherical bob, which is to be called as a spherical bob, spherical in shape. So as it is a symmetrical in shape, the whole mass of that bob will be concentrated at a single point. So we can consider it as a point mass. The simple pendulum is a pendulum in which a point mass is attached to a string which is light in weight and inextensible. That is nothing but the concept of simple pendulum. Now, this simple pendulum, the string, one end of the string is attached to a rigid support, which I am going to call it as a position, as a P. And this O is nothing but the mean position of this pendulum. Now, the distance between point of support to the center of bob, or the point of support to point mass of the bob, this length is to be called as a length of simple pendulum. So this length of simple pendulum, I can say that, which is denoted by letter capital L, which is nothing but length of the string plus radius of that bob. Why radius of the bob is added? Because at the center of this bob, whole mass is concentrated. So that's why that R distance will be added to the length of the string. So that total length is to be called as the length of simple pendulum. Clear? Now, when this bob is at the mean position, at that time, the two forces will be going to be act on this pendulum. What is the first force? First force is the weight of this bob, which is acting vertically downward, which is nothing but the weight of the bob, mg. And the second thing is nothing but tension imparted to the string, that is nothing but the P dash. Now the direction of tension will be towards the rigid support and weight of the bob, which is acting vertically downward. So tension on the string and weight of the bob, they are exactly opposite in direction. So that both the forces will get balanced. And therefore your pendulum will remain at rest position. But to this pendulum, whenever we are applying a certain force, so I am going to apply a certain force on this bob. So when I apply a certain force on this bob will get displaced to a certain position. This simple pendulum will get displaced to a certain position. And it will attain the new position as A. So your bob, due to force, bob will get displaced to the position as A. So this A position, I am going to call it as the extreme position of this bob. Now when this bob is at extreme position by making certain angle theta with the rigid support, at that time the corresponding displacement of the bob is x. And when this bob reaches to extreme position, at the extreme position, now again two forces. One force is tension towards the rigid support along the string, and another is nothing but the weight of the bob, which is vertically acting downward, that is mg. Now see that your T dash, that is the tension of the string, and mg. They are not exactly opposite. And therefore now, this mg component you have to resolve into two. So what I can say that the two forces are going to be act on the bob. One is tension T dash. Second is nothing but the weight of the bob, which is nothing but the mg. But this tension and weight of the bob mg, they are not exactly opposite. Therefore, I have to resolve the two components of this mg. One is nothing but the adjacent component, which is nothing but the mg cos theta. Now see here, this is the weight is vertically acting downward. So this parallel line and length of the string parallel line. This is the transverse. Therefore, these two are nothing but the adjacent angle. Therefore, this angle is also theta. So this component is adjacent to theta. Therefore, its value is mg sin theta. And the second component is perpendicular to the string of the pendulum, which is nothing but your mg sin theta. Means your mg component will get resolved into two. One is nothing but the mg cos theta, and the second is nothing but the mg sin theta. Now this mg cos theta component is away from the rigid support, and towards the component, force component is nothing but T dash. Means T dash component will be balanced by mg cos theta. While mg sin theta direction is towards the center, towards the mean position. Right? Means this mg sin theta restores the position of the bob back to its original one. And therefore this mg sin theta will be giving a restoring force. It is towards the restoring force. And this mg cos theta is exactly balanced by the tension imparted to the string. Therefore, now what I can write here? I can write down mg sin theta is equal to nothing but the restoring force. But the direction of mg sin theta is towards the mean position. So I can use here the minus. So minus sign indicates that the direction of mg sin theta component is towards the mean position. So now I can concentrate on this equation. And using that equation, now I can find out the period of this simple pendulum. Clear? So now this component I can write down, this value I can write down, F is equal to minus mg sin theta. Now this force F, according to Newton's laws of motion, the force is nothing but mass into acceleration, which is equal to minus mg sin theta. From both sides, this m component will get cancelled. So I get it. Acceleration A is equal to minus g sin theta. But A is equal to minus g sin theta, where this theta is nothing but the angle made by the pendulum. If this value of theta is very small, then this sin theta can be written as simply theta. And therefore your acceleration value I can write down acceleration A is equal to minus g theta. Clear? Now I can write for this theta using your definition of angular displacement. So in angular displacement we have seen that angular displacement theta is equal to arc length divided by radius. So I can say that theta can be written as arc length OA upon radius. Radius is nothing but the length of simple pendulum. And this arc A can be written as, this theta can be written as x upon. Now this value of theta I can substitute in the acceleration expression. So your acceleration expression, now this acceleration expression I can write down. Acceleration A can be written as minus g x upon L, where g is nothing but the gravitational constant and L is nothing but the length of simple pendulum. In simple pendulum, length is inextensible. In this, L will remain constant, G will remain constant. Is what I can say that acceleration is equal to minus G, or acceleration is directly proportional to when your G and L are constant. So when your G and L are constant, your acceleration is directly proportional to. Now what this indicates? This indicates that motion of simple pendulum is a linear simple harmonic motion. That we have seen in the first lecture of oscillation. That is in linear SHM, acceleration acting on the particle is directly proportional to the displacement. And direction of acceleration and direction of displacement are opposite to each other. So same concept I am getting in this example. So from this, what I can say that, from this equation I can say that the motion of a simple pendulum is nothing but the linear simple harmonic motion. So this is one of the questions which can be asked for 3 marks. Show that motion of a simple pendulum is linear simple harmonic motion. To show that, you have to prove up till this. Clear? And now, from this point, now I can go for the period of simple pendulum. So now, in that period of simple pendulum, I can say that period t, which is equal to nothing but 2 pi upon omega. This is the formula. Where t is equal to 2 pi under root of this, instead of omega, I can write down omega is nothing but acceleration per unit displacement. Right? This we have seen in very initial first concept. If you are remembering, that is in differential equation we have substituted omega is equal to k upon m. If you are remembering, in that this k upon m is nothing but acceleration per unit. This is omega step. So simply omega is nothing but acceleration per unit displacement. So I can write down this acceleration per unit. Clear? Now, this acceleration per unit displacement I can write from this equation. Acceleration A is equal to minus g x by L. So that equation I can write down acceleration per unit displacement means A upon x. This x I will take for the division, which is equal to nothing but minus g by L. What does minus sign indicate? Minus sign indicates direction. Right? So if I consider only magnitude, what I write? A by x is equal to g by L by considering only magnitude. So A by x is equal to g by L by considering magnitude. So this acceleration per unit displacement value I can substitute as a g by L. So the period will become period t is equal to 2 pi under root of, what I will say here, g by L. Means what I am getting, period of simple pendulum case 2 pi under root of L by G. So this is nothing but your derivation of period of a simple pendulum. And now from this derivation, what we can conclude? The first conclusion, that is period of simple pendulum is directly proportional to the square root of length. This is my first conclusion. Second conclusion, period of simple pendulum is inversely proportional to the square root of acceleration. Right? Then, third conclusion, in this period formula, mass of the bob is not included. Whatever may be the mass, the period formula will remain same. Means what I can say that for this period formula, the period is independent of mass. And fourth conclusion, I can say that this period also doesn't consist of the amplitude of the oscillation. So what I can say that T independent of amplitude of the oscillation. So these are the four conclusions we can draw. And this is to be called as the laws of simple pendulum. And there are so many numerical MCQ, very short answer, will be related to this four conclusions. So what is the first conclusion? What is the first formula for the period of simple pendulum? Period of simple pendulum T is equal to 2 pi under root of L by G. From that, what is our first conclusion? Period is directly proportional to root L. L is nothing but the length of the simple pendulum. Another, period is inversely proportional to the square root of G. Third conclusion, period formula doesn't consist of term as a M, that is the mass of the ball. So we can say that period of simple pendulum is independent of mass. Also, it doesn't consist of a term as an amplitude. So what we can say that period is independent of amplitude. And these four conclusions are to be called as the laws of simple. Clear? So this is also your one of the 2-mark question or MCQ or very short. Get it? So here our concept of period of simple pendulum will get mentioned. Now from this formula of period of simple pendulum, one more concept I can get it here, which is to be called as a seconds pendulum. So we have one of the concept, seconds pendulum. Now what the seconds pendulum is? The pendulum whose period is equal to 2 seconds. That type of pendulum is to be called as a seconds pendulum. So period of pendulum T is equal to 2 seconds is called as a seconds pendulum. Now what we are knowing? For simple pendulum we have a formula T is equal to 2 pi under root of L by G. In this formula I can put T value as a 2. So 2 is equal to 2 pi under root of L by G. From both sides this 2 factor will get cancelled. What is remaining? 1 is equal to pi under root of L by G. I can square both the sides, left hand side and right hand side. So if I square it, I will get it 1 is equal to pi square L by G. And therefore, the length of seconds pendulum Ls can be written as, here I can say that it is written as G upon pi value is a constant. Pi value is nothing but 3.147. So what I say that Ls, length of second pendulum, is directly proportional to G. And all of you are knowing that in the 11th standard we have seen that the G value, that is gravitational acceleration value, changes from place to place. So if the place will goes on changing, value of G changes. And if the value of G will goes on changing, the length of the second pendulum will also goes on changing. So there may be a 2-mark numerical problem depending on this formula. Very short answer depending on this relation, or MCQ question. Now you know the very common question. Earth is a sphere, but actually not it is a sphere. Earth is bulge at the center. The equatorial radius is maximum, pole radius is minimum. And therefore, we are knowing that what is the difference in the gravitational acceleration at equator and gravitational acceleration at the pole. And I think in 11th standard you have seen this formula, that is G is equal to capital Gm upon R. So at the equatorial, radius is maximum, means G is minimum. So at the equatorial, gravitational acceleration, G value is minimum. If G value is minimum, then the length of the second pendulum at the equatorial is minimum. So just remember this concept, that is along equator, length of the second pendulum is minimum as compared to pole. Because along the pole, radius is minimum. Radius is minimum means G value is maximum. If this G value is maximum, means length of second pendulum at the pole is maximum. So, like that manner, this simple pendulum concept is important regarding 3-mark question, 4-mark question, 2-mark question, very short answer of 1 mark, and MCQ question. Now, what type of questions will come first? The very first question I have told that. Let us show that motion of simple pendulum is a linear simple harmonic motion. Second, derive expression for period of second pendulum. Third, laws of simple pendulum. And fourth, the length of second pendulum. And in between that, all the formula gives us very short answer and MCQ question. Clear? So this is about your concept of simple. Fine? So you have to remember this period formula carefully. Period of simple pendulum as well as the length of second pendulum. So these two formulas are important for your numerical. Clear? So here our simple pendulum concept will get finished. Fine? Now, after this simple pendulum, now we are going to start the new point. That is nothing but the angular passage. Now, what is angular passage in concept? Now, in this angular passage in concept, we can concentrate on a device which is to be called as a torsional pendulum. Now see this is the third type of pendulum you are studying. In 11th standard you have seen conical pendulum. Then just now I have explained simple pendulum. And this is nothing but the torsional pendulum. Now what this torsional pendulum is? If I am considering this is a rigid support. Here is a metallic string. And to that metallic string, a metallic disc is attached. And when I am giving certain, if I apply a on this metallic disc, then this metallic disc will start rotating about an axis of rotation. So here, this, what I can say here, this pendulum will rotate about an axis of rotation, which is passing through the center of this and perpendicular to the plane of the disc. And it will start performing rotational motion. So that type of pendulum is to be called as a torsional pendulum. Now in this torsional pendulum, when this pendulum starts rotating, so when it will rotate, for rotational motion, it requires a torque. And this torque is nothing but I into alpha. That we have already studied in your rotational dynamics. You have seen that whenever any body is performing a rotational motion, for the rotational motion, it requires a torque. And whenever a torque is acting on any particle, at that time, it will perform a rotational motion with a certain angular acceleration alpha. And therefore, your toe is nothing but the toe is equal to nothing but your I. Clear? So now this is your one of the equation for the torque. And now I can say that in the angular SHM, while performing the angular SHM, what I can say that when a torque is going to be act on the pendulum, that torque must be equivalent to restoring torque acting on the pendulum will be nothing but for the angular displacement of the this disc of this torsional pendulum. So here is nothing but the angular displacement. So now we can see the equivalence. Yeah. If we are considering that is in linear SHM, we have seen that your force F is nothing but equal to minus Kx. That is in the linear SHM. So in angular SHM, I can say that tau is equal to minus C into theta, where C is nothing but the restoring constant and theta is nothing but the angular distance. So this is already we have studied in linear SHM. For linear SHM, force is required. For angular SHM, a torque is required. Right? So in linear SHM, force is equal to minus Kx. Therefore, in linear SHM, torque tau is equal to minus Ct. C is nothing but the torsional constant, theta is nothing but the angle. Now you have these two equations. This is equation 1, here is nothing but your equation 2. Now from this equation 1 and 2, both the equation left hand side gives the torque. Therefore we can equate equation 1 and 2. And if I equate your equation 1 and 2, I can write down I alpha is equal to minus C into T. Right? Now here this I is nothing but your moment of inertia. Your alpha is nothing but your angular acceleration. So I can say that I is the moment of inertia. Alpha is the angular acceleration. Angular acceleration I can write down d square theta by dt square, which is equal to minus c theta. Therefore, what I can say that this equation I can write down d square theta by dt square is equal to minus c upon I into theta. Now this c upon I is nothing but what? Torsional constant per unit moment of inertia. So this torsional constant per unit moment of inertia means what I will say that this is equivalent to d square theta by dt square plus this quantity I will make it plus, which is equal to c upon I into theta, which is equal to 0. and this is to be called as your differential equation for the angular. So this is your differential equation for angular section. Now if this equation you will compare with your differential equation of linear section, d square x by dt square plus omega square x is equal to 0. This is your differential equation for linear section, and this is your differential equation. This is for angular section. And here is the equation for, this equation is for linear. Now see here, d square theta by dt square, this is the angular acceleration. D square x by dt square, this is the linear acceleration. Theta is the angular displacement. X is the linear displacement. Means what I can say that this omega square is equivalent to c by r. And what is omega square? Omega square is nothing but your acceleration per unit distance. Means in linear, in this angular acceleration, I can say that in this angular acceleration, angular displacement or angular acceleration per unit angular displacement can be written as which is equal to nothing but c upon. So under root of angular acceleration per unit angular displacement is equal to nothing but the under root of c upon. And now this I can use the equation in the period of angular acceleration. So what I can say that the period of angular acceleration t is equal to 2 pi divided by under root of what I say that angular acceleration per unit angular displacement. So what I say that t is equal to 2 pi divided by under root of c upon r, where c is the torsional constant, r is nothing but the moment of inertia. So this is also your one of the formula for period of angular. Clear? So now, in the first lecture of oscillation, we have seen the formula for period of strain. Okay, here in the first lecture we have seen the formula for period of strain. T is equal to 2 pi under root of m by k. This is the period of strain. This is the period of angular acceleration. And also we have seen the period of linear acceleration, that is simple pendulum, 2 pi under root of L by G. And in the previous rotational dynamics, we can have seen the period of conical pendulum. That is period of conical pendulum, T is equal to 2 pi under root of L cos theta upon G. So these are the total period formula which you have seen in case of an. Clear? So don't get confused. This is first formula for period of angular acceleration. This is the formula for period of spring. This is the formula for period of simple pendulum, or I can say that period of linear. And here we have solved the differential equation for angular. Get it? So this is your 2 mark question. Derive expression for differential equation of angular section. So your differential of equation of angular section, for that purpose we can solve by this. That is torque expression. Torque is equal to I alpha. In equivalence with linear section, In case of angular extension, we can write tau is equal to minus c theta, where c is the torsional constant, and then we can compare equation 1 and 2 by equating the right hand sides. In that, I can put value of alpha as the d square theta by dt square, and from that, I can solve the differential equation of omega. Clear? Any doubt? Fine. So now I'll stop my lecture. In the next lecture, we can see the example of angles. Thank you.